Hi everyone, my name is Gautam Choudhary. I'm a master's student at Purdue University and I'm delighted to present our work with Adobe Research. Our paper, titled as PersonaSAGE, a multi-persona graph neural network, is a joint effort with my co-authors Ifti, Eunyee, Fan, and Ryan from Adobe Research and Databricks. This work presents a novel multi-embedding approach for network data. Imagine a social network where users engage across various platforms such as Facebook, Twitter, WhatsApp. Each user exhibits a unique level of activity on these platforms. As computer scientists, our goal is to capture this diversity and construct distinct user representations, ideally tailored for each platform. In our scenario, illustrated by John's activity in the figure, we observe varying degrees of engagement on these different platforms, which we define as personas. Our objective is to uncover and learn these individualized user personas within a network. It is important to note that users may interact with one or more such platforms, leading to a diversity not only in the personas themselves, but also in the number of personas per user. To concretize the challenge, we represent social networks as graphs, with nodes and edges symbolizing user interactions, and our aim is to learn a set of embeddings for each node, emphasizing the word set for the reasons we'll discuss in the next slide. In the image shown for John, we observe the presence of three personas, one each for Facebook, Twitter, and WhatsApp. The problem of learning node embeddings has been widely studied in the literature under graph neural nets. Many architectures have been proposed, such as Node2Vec, GraphSAGE, which gives a single embedding for each node. ASP2Vec is a multi-embedding approach which yields multiple but fixed number of embeddings for each node. In our work, we relax this assumption and instead learn sets of embeddings where the cardinality of each set may be different. And as we saw in the previous slide, this flexibility in the number of personas is desirable property to model a realistic environment. Therefore, we make the following three contributions through our work. First, we identify and mathematically formulate this notion of learning multiple personas. Second, we come up with a solution by proposing a novel framework called PersonaSAGE, which automatically learns personas in a graph. Third, we also benchmark our method with a wide variety of baselines and multiple downstream tasks such as link prediction and node classification. Given an arbitrary graph G, the objective is to learn a set of embeddings xv, x1 through xk for each node v, where for any two different nodes u and v, their number of personas may be different as shown via the inequality. That is, different nodes may have different number of embeddings. The next constraint suggests that the embeddings learned for any node in a graph are unique or non-identical. Without loss of generality, all embeddings are assumed to be in a fixed d-dimensional space, and at most there are k different personas where k is pretty less than the total number of nodes in the graph G. Intuitively, each learned embedding xi represents a persona for that user. Our solution goes as follows. The input is a graph G consisting of nodes and edges. Without loss of generality, we assume an initial set of given node features. In case they are missing, we can always use random embeddings to begin with, which will be fine-tuned in the training process. And we'll see more of this in our experimental results. PersonaSAGE is a two-step process. In the first step, we do an offline clustering of nodes, perhaps based on their node features, to arrive at an initial persona assignment for each node. Let's say we hypothesize that we want to mine 4 personas, thus we run weighted k-means with 4 clusters to arrive at a 4-length vector for each node representing their persona memberships for each cluster or persona. Now, for each node, by using an initial node embedding and persona embedding and persona membership vector as input, each layer of PersonaSAGE iteratively updates them based on the neighboring nodes, as highlighted in step 2 in the figure. The core idea behind is to perform an aggregation of persona embeddings of a reference node, here A, and that of its neighboring nodes, here B, C, and E, and learn this through a common neural network shared across all the personas, thus saving parameter costs. We highly encourage to read our pseudocode to understand the implementation behind. Similar to various aggregation strategies that can be applied in a graph neural network, we investigate and define 3 aggregation functions that take into account the personas. Each of these describe how the persona membership value C, which is a scalar, combines with its own persona embedding XU, and how does it interact with the corresponding neighborhood embeddings. In the mean aggregation, we scale the persona embeddings with the corresponding persona membership values and then perform an average. This is the default strategy used for the experiments. The sum and max aggregators are also defined in a similar way. We investigate the efficacy of our proposed model through various experiments. We utilize 3 widely used graph datasets as shown in the table: Quora, CiteSeer, and PubMed. We benchmark against 7 baseline approaches, some of which are Graph Convolution Network, GraphSAGE, and Graph Attention Networks, each producing a single embedding. Note that for a fair comparison, the size of the final embedding is same for all the methods. That is, if our method produces 5 persona embeddings, each of length 10, which become 50 after concatenation, then for each of the baselines, they also output a 50-length single embedding. In addition to the 2 widely used tasks for link prediction and node classification, we also present a case study for item recommendation. Adam Optimizer coupled with cross entropy is used for optimization, and the evaluation metric is AUC, which works best even in case of imbalanced data. All experiments are run with 5 different seeds and average results are reported. We first evaluate PersonaSAGE for link prediction. In particular, the goal of link prediction is to accurately predict the likelihood of the formation of new edges in a graph. This task measures the capability of the embeddings to capture the structure and topology of the graph. In Table 2, we compare PersonaSAGE to its baselines. There are 2 scenarios considered for a given dataset. One where the input features are present, and 2 where they are absent, in which case they are randomly initialized. We observe that PersonaSAGE outperforms the other methods across all graph datasets and across both feature settings. Interestingly, PersonaSAGE performs best on CiteSeer and Quora when input features are randomly initialized, as opposed to using the standard features that are typically used for node classification. In Table 3, we evaluate a few different variants from the proposed PersonaSAGE framework. Notably, we observe that these different variants often outperform the previous variant in Table 2. For instance, PersonaSAGE KM Max variant that uses k-means with the max aggregator performs the best on PubMed. Furthermore, while there's not a single PersonaSAGE variant that always outperforms best across all graphs and input features. The variant that uses k-means with the mean relational aggregator outperforms the other variants most consistently. In particular, this variant always performs best when using the actual input features compared to using random input features, which models the case where such features may not exist in the input graph. Now, we investigate using PersonaSAGE for the node classification task. In Table 3, we observe that PersonaSAGE always outperforms the other methods across all benchmark datasets. For node classification, we only use the raw input features since they are known to be correlated with the class labels we are predicting for. From Figure 1, we observe that PersonaSAGE achieves the best performance compared to other methods even when a modest number of epochs are used, here only after 40 epochs. To further scrutinize, we evaluate impact of the maximum number of persona embeddings per node k by varying this hyperparameter from k equals to 1 to 10. For this experiment, we use PersonaSAGE variant that leverages k-means with the mean aggregator. We ensure the final embedding size remains constant by reducing the size of the persona embedding obtained. Results are reported in Figure 2 for both link prediction and node classification. Overall, we observe that for link prediction, the performance generally increases for Quora and CiteSeer, while remaining approximately same for the PubMed. In contrast, node classification performance of CiteSeer is best when k equals to 4, then decreases as k increases further, whereas the best performance on Quora is for k is equal to 2 and remains approximately same for the CiteSeer. These results indicate the utility of PersonaSAGE and its ability to learn multiple embeddings per node in the graph. We also experiment PersonaSAGE to recommend different types of entities from a usage log data of a data management system. Such user interaction logs contain the data queries executed, the datasets used, along with the attributes selected in those datasets. And the goal is to leverage user interactions with the platform for building a personalized recommendation engine for datasets, queries, and attributes. Results for 3 different personalized recommendation tasks, including query, attribute, and dataset recommendation, are provided in Table 5. Overall, we observe that PersonaSAGE outperforms the other methods across all 3 personalized recommendation tasks. The improvement compared to the next best method across the 3 recommendation schemes is significant. It's around 20% in query and dataset recommendation. In summary, our work introduces an innovative method for modeling the polysemous nature of users or nodes within a social network. Our proposed method, PersonaSAGE, takes a unique approach by learning multiple persona embeddings per node, accompanied by their respective persona weights. Through extensive evaluations across various application tasks such as node classification and link prediction, PersonaSAGE consistently outperformed other methods across diverse graph datasets. Looking ahead, we aim to benchmark PersonaSAGE against existing multi-embedding approaches to further validate and refine our innovative method. Thanks everyone for attending our talk, and we would be happy to hear your thoughts, feedbacks, questions you may have. Thank you.